Hello. We last talked about converting between decimal and octal and decimal and hexadecimal, and today what you're going to look at is a shortcut way of converting between binary and octal and binary and hexadecimal. Before now, if you wanted to convert a number from binary to octal, you would have to convert from binary into decimal and then the decimal number into octal. But because of the way powers of 2 work, there's actually some really quick and easy shortcuts for converting between binary and octal and binary and decimal. And we're going to go through those today. And this actually works with any base that was a power of 2. So if you had a base 4, base 32, base 64 number, it would work. And it goes back to what we talked about a little bit about how I can cycle through. So if you notice that if I go through 2, my first kind of cycle of octal numbers, when I get all the way through from 0 to 7, and I get through a cycle, I've gone through every possible option of 3-digit binary numbers. Every combination of zeros and ones, 3 digits in binary, is covered in one set of octal numbers. And if I look at it even further, and I look at to get through one cycle of hexadecimal numbers, so from 0 all the way to F, so one cycle of hexadecimal numbers, then I go through every possible combination of 4 zeros and ones, 4 binary bits, every combination of 4. So we're going to see that I can quickly and easily convert between the two of them using kind of the shortcuts I've just highlighted. So starting with octal, we know that there are 8 possible digits from 0 to 7, and if I go through every single possible 0 to 7, when I look at it in binary, it's every possible combination, permutation of zeros and ones in a 3-digit binary. And remember, I can always pad in front of any of those values. So going through this, looking at it, I can display all of those digits with a 3-digit binary. So one way to do the conversions is I can either just draw this table out and kind of every time I go through it, remember what they are. I can also kind of draw out and remember that if I have a 3-digit binary, that first digit, that least significant bit, represents 1. My next significant bit represents 2. The next significant bit represents 4. So I can just kind of draw out 1, 2, 4, and then figure out what I need. If I do 4 plus 1, that would give me 5. So I don't need a 2-bit. And you kind of just go through that same process, and you'll see that it works for all of my values. So if I wanted 3, I would do 1 plus 2. I don't need any 4s. If I wanted 4, I would start with a 4, no 2s, no 1s. If I wanted 2, it would be no 4s, a 2, and no 1s. And I can go through and do it the same if I want to go the opposite way. So let's say that I have a 3-bit binary, and I want to figure out what that is equivalent to in octal. And well, that's pretty easy. It's obviously going to be 1. And if I take a look at some more examples, I can see that all I have to do is kind of add up those values. 4 plus 0 plus 1 gives me 5. 4 plus 2 gives me 6. 4 plus 2 plus 1 gives me 7. And I could look those up in my chart as well. So how does this make it quicker? Well, if you have a larger binary number like this, I just go through and I'm going to chunk this into groups of 3, and then I could just write my 1, 2, 4 down here at the bottom, or just kind of, and then repeat it, 1, 2, 4, 1, 2, 4, and I go through, and each of these is going to give me a different digit in my answer. And there are 3 groups of 3, so my octal number will have 3 digits. So 2 plus 1 is 3, 4 plus 2 plus 1 is 7, 4 plus 2 is 6, so my octal equivalent is 673. I come down to my next one. Again, I break it down into threes. Remember that if I'm short, I can always just pad with extra zeros, but obviously this one's just going to be 1. This one will be 2 plus 1, so that's a 3. This is the same value, and this one is just a 2. So I get 1, 3, 3, 2. Now you have to be careful when you're going back the other way. Remember, I always need 3 binary digits when I'm doing this conversion. A lot of people very quickly and easily will get messed up because they don't put 3. So this has to have 3 digits. So that my 2 has to have 3 digits. My 5 has to have 3 digits. Oops. My 5 has to have 3 digits. And then my 3 can have 3 digits or doesn't have to because it's the most significant. But to get a 2, I would just add up a 2. 5 would be 4 plus 1. 3 would be 2 plus 1. And if you want to, you can always pad on an extra 0 at the beginning. And so again, I always want to make sure this is going to be 4, this is going to be 1, this is going to be 7. So if I was creating 4, that one's easy, it's just 1, 0, 0. If I'm creating 1, that one's easy, 0, 0, 1. And 7, I could also look at my table and know that's 1, 1, 1. So that's a quick and easy way of converting between octal and binary. And I'm pretty much going to follow the same process, the same algorithm here with my hexadecimal to binary conversions, except that remember I have 16 possible digits, 0 through 9, and A through F. My highest digit again is F is 15, takes up 4 binary digits. And if you look at my table, I've gone through every possible combination of zeros and ones with 4 binary bits. So I can display those, which makes this shortcut work. It's a really easy way to do it. Those conversions of having to convert all the way into decimal. And again, this one is going to work both ways. So if I take my first example here, let's say I want to convert B into binary. So I've got B, my hexadecimal value, which I know is also equal to 11. Well, how do I get 11? I would take 8 plus 2 plus 1. It's going to give me 11, which I can check is equivalent over here on my table. Some other examples. Remember, these always have to be in groupings of 4. So if I have a value like 5 that doesn't need this 8-bit, I still have to put a 0 there so that my number doesn't get messed up when I do my conversions later. And with a 9, it would be an 8 plus 1. And just like with going between octal and binary, this works both ways. So 8 plus 2 is 10, which is going to give me the letter A. 2 more examples real quick. 8 plus 4 plus 2. 8 plus 4 is plus 2 gives me 14, which is almost my last hexadecimal digit, but it's not. And then this one, I don't use the 8, but I've got 4 plus 2 plus 1 is 7. Again, remember, I don't want to lose this 0 because all of those have to be in groupings of 4. If you lose that 0, you're going to end up with problems when you go to convert later on. So, taking a look again, I can do my shortcut 1, 2, 4, 8 when I go through and group by 4s. So I chunk this into 4s. I could go in and say 1, 2, this one's a 4, I don't need to add it. And then 8, well 8 plus 2 is 10, plus 1 is 11, which I know is the letter B. I go and look at my next one, 1, 2, 4, that one's pretty easy. 1, 2, 4, 8, so 8 plus 1 gives me 9. Quick and easy conversion. This only, though, works between bases, my binary, and then bases of 2. Sorry, powers of 2. So taking a look here, 1 plus 2, no 4 plus 8, 8 plus 2 is 10, gives me A. This one is just the 8, which makes it easy. This one's going to be 8 plus 2 plus 1, gives me 11, which is B. And then I can always pad on a 0 here, but I don't really need it. 1 plus 4 is 5. Conversion done. And again, with these values, I know that they're less than 8, but I have to make sure that I represent them with 4 binary digits. So if I come in here and I say 25F3, this still has to take up 4 spots. This value has to take up 4 spots. This one needs to take up 4 spots. If you skip one of those, then it's going to shift all of your values down and you're going to end up with a different number. So a 2 would be easy. 5 is just 1 plus 4. F I know is 15, which is my highest digit, highest value, so it's going to be all 1s. And then 3 is just 1 plus 2. And then I can pad on the zeros. I got one more example here. Doing a quick and easy conversion, I've got 4, which is C, remember, which is going to be 12. So it's going to be 8 plus 4. B, which is 11. It's going to be 8 plus 3. And then 9, which would be 8 plus 1. Now, a quick and easy way to remember, is it 2 digits? Is it 3 digits? 2 to the 4 equals 16. So that 4 right there tells you that I need 4 digits when converting from binary to hexadecimal. And the same is true if I think to my octal values. 2 to the 3rd equals 8, and I needed 3 digits in that conversion. So you might see problems like this, where you have a value in one base and you're asked to convert it into all the other bases. And you really can go different ways. One of the easiest ways to get my octal is going to be to go first to binary and then convert from binary to octal. How you get your decimal value is completely up to you. You could convert it straight from base 16. You could convert it from your binary. You could convert it from your octal. Any of those 3 you can go through to convert to your base 10. But there is no shortcut directly from 16 to 10. So I like to go ahead through and go from my base 16 into my base 2 and then convert into my other 2 bases. So I've got 2, 0, F. So 2 would be, there's my 4 values for 2. 0, I have to put all 4 of those zeros in. And then F is going to be 4 1s. Now I can come back in, and to do my octal, I'm going to do groupings of 3. So slightly different. I have to make sure I'm careful when I go through and I do my groupings of 3. This one's going to be 2, this one's going to be 0, this one will be 4, and this one's going to be 7. So in a matter of minutes, I've gone ahead and converted into 2 of my extra bases, and then I can go into my base 10. I could either convert it from here. I could go in, if I want to review, this is going to be 2 times 8 to the 0 plus 0 plus 4 times 8 squared plus 7 times 8 cubed. This will be 2 times 1 plus 0 plus 4 times 64 plus 7 times 512. So this is going to be 2 plus 0 plus 256 plus a really big number here, 3,580. 84. And when I add all of those up, I get 3,842. Again, quick way to remember, looking that make sure you're kind of on the right track. This value should look larger than this value because it's in a larger base. This 3,842 should look larger than the 7402 that's in my octal base, and looks a lot smaller than my value here in binary. So to convert here, I start out with the value in base 10. I can convert into any of these if I want to divide by 8s, if I want to divide by 16s, if I want to go ahead and divide by 2s. I could go through and figure out my 1, 2, 4, 8, 16, 32, 64, 128, and know that, okay, 155 minus 128, so I have a 128, that's going to give me 27. Okay, so no 64s, no 32s. I can subtract 16. Gives me 11. I can subtract 8. Gives me 3. No 4s, a 2, and a 1. And then I can easily come back through and do my chunking. Groups of 3. Here, so I get 3, 3, 2. And then come back in one more time and do groupings of 4 to convert into hexadecimal. So I get 8 plus 2 plus 1, so it gives me 11, which I know is B. And then over here I get 8 plus 1, which is 9. And there's my conversion. So the trick is, when converting from binary to octal, know that I have to go into groupings of 3. When I'm converting from binary into hexadecimal, I have to go into groupings of 4. Quick and easy way. There is no shortcut getting from base 10, but once I get into either octal or binary or hexadecimal, I can easily convert between those three using the shortcuts in this video. Good luck!